Okay, let's unpack this. Amazon, we all know them for, well, shopping,
Yeah.
obviously, and AWS cloud computing.
Right, that massive $100 billion business, huge valuation, $2 trillion.
Exactly. But now, maybe surprisingly, they're right in the mix with quantum computing, alongside the big names you usually hear, like Google and Microsoft.
Yeah.
So the question is, how did they get here? And what does this quantum push actually mean for computing and maybe even for your everyday life down the road?
It's fascinating, isn't it? Another tech giant jumping into this, well, already quite crowded field. Today, we're doing a deep dive into Amazon's quantum efforts.
Hmm.
We're basing this on a recent look inside their AWS Center for Quantum Computing, which is actually at Caltech.
Oh, interesting location.
Yeah, and our mission really is to understand their strategy, the tech they're building, how they compare to the others,
Right.
and crucially, what quantum computing could actually do. It's not just about these tech giants, right?
Yeah, absolutely.
It could change whole industries, maybe solve problems we currently think are impossible. So for you listening, the goal here is to get the significance of Amazon's move.
Okay.
Without getting totally lost in the super technical quantum physics, we want to focus on the why it matters, those aha moments.
Got it. So Amazon's quantum leap, it really does feel like a big step. AWS was, a game changer for them.
Totally.
Now, quantum, what's the connection? What's the logic driving this?
Well, if you think about how Amazon evolved, especially with AWS, this quantum move actually fits their model pretty well.
How so?
Think about AWS. It provides computing resources off-premise through the cloud, right?
Right. Pay as you go, scalable.
Exactly. The vision for quantum is kind of similar. Offer quantum computing power the same way, accessible via the cloud.
Ah, okay. So quantum becomes like another service layer in AWS.
Potentially, yeah, a sort of supercharged part of AWS for tackling these incredibly difficult problems that classical computers just choke on.
Hmm.
So democratizing access, making powerful tools available, that seems core to their thinking, just like with AWS.
So it's about replicating that cloud success story, but for quantum.
That seems to be a key insight, yeah. Take that model, apply it to this new powerful technology.
It's interesting, though, because you do hear Google and Microsoft mentioned more often, perhaps. It feels like Amazon might be, I don't know, a bit late to the party.
That's a fair
That
observation.
put them way behind.
Well, Microsoft's been looking at quantum for, gosh, almost 2 decades. Google is seriously since about 2012.
Right.
And it's true. For a few years, Amazon wasn't making as much noise in the quantum space. But here's the thing.
Yeah.
Quantum computing is still so early. It's very much R&D territory.
Okay, so it's not like the race is already won.
Not at all. Others have more research years under their belt, sure. But the field is so new, so dynamic, that coming in now with serious investment doesn't mean they can't succeed.
Hmm.
It's maybe less about being first and more about having the right approach, or maybe even a better one eventually.
But what about talent? And catching up on research. Google and Microsoft must have a head start there, attracting scientists, building knowledge. Isn't that a huge hurdle?
It's definitely a crucial point. Early movers do have that advantage. But remember where Amazon put their center?
At Caltech, you said?
Exactly, right? In a major hub for quantum science. That suggests they're being strategic about accessing talent and tapping into that existing ecosystem.
Okay, so embedding themselves in the research community.
Right. And sometimes, a fresh perspective coming in a bit later can actually lead to different ideas, maybe finding paths others overlooked. Strategic partnerships and talent are key, and they seem focused on that.
All right, let's get into the details then. Inside Amazon's quantum R&D at Caltech, what are they actually doing there? What does building one of these machines look like?
Well, being at Caltech puts them right in the thick of things, scientifically. The inside look showed some basics, like those big fridges.
The dilution refrigerators, right?
Yeah, exactly. Essential kit. They're needed to get things incredibly cold, which stops environmental noise messing up the quantum states.
Okay, so the fridges handle the cold. They mentioned electronics sending signals down inside. What happens there?
Right. So electronics outside generate really precise microwave signals, control pulses. These travel down special wires into the coldest part of the fridge. And right at the bottom, that's where the quantum processor sits. It receives those instructions.
And Amazon has their own chip now.
They do. Their first in-house one, nicknamed Ocelot. And the big claim they're making is about its architecture.
What about?
They say it's designed to be scalable and could reduce the need for error correction overhead by, well, they said up to 90%. That's a big number.
Wow, 90% reduction in error correction needed. That sounds huge.
It would be. Now, Google's also making progress here with their Willow chip, focusing on reducing errors too. So it's
Yeah.
definitely a hot area of competition.
So both Amazon and Google seem to be focusing hard on building chips that are inherently less error-prone.
That seems like a key takeaway, yeah. Shifting focus towards building better fundamental components, not just relying on fixing errors after the fact.
Before we dig more into errors, tell me about these cat qubits in Ocelot. Cool name, Schrodinger's cat.
Yeah, it nods to the famous thought experiment, but we don't need to get lost in the paradox.
Okay.
The important thing about these cat qubits is they're a different type of qubit. In Amazon's version, they have this macroscopic nature.
Macroscopic, like bigger.
Sort of. At the fundamental quantum level, the electrical signals, voltages, currents involved are larger than in some other qubit types.
And why does that matter?
It seems to make the quantum information more robust, more resistant to noise and errors, like turning up the volume on the quantum signal so it doesn't get drowned out as easily.
Interesting. So a hardware-level approach to fighting errors. That sounds like a key difference.
It could be, yeah. A potentially significant differentiator if it works out well at scale.
They also mentioned other chip formats, something called 76P.
Right. That was described as more of a previous workhorse. Suggests earlier designs, maybe testing different ideas. The move to Ocelot implies a shift towards these potentially larger, more complex formats designed for better error performance and density.
Got it. And the temperature. Just remind us how cold we're talking.
10 milledegrees above absolute zero, 10 millikelvin. They compared it to the deepest, coldest part of outer space. It really hammers home how delicate these quantum states are.
Absolutely. Just incredible engineering needed.
For sure. And maintaining that cold is vital for the processor itself, which is essentially this grid, this array of physical qubits. And the real intellectual property, the secret sauce, as they put it, is how that array is designed, how the qubits are laid out, how they're controlled, how they talk to each other. That's where the magic and the competition lies.
Okay, which leads us right into the big challenge. Errors and scaling. You mentioned noise sensitivity, vibrations, heat, even Earth's magnetic field. Keeping these things stable sounds like nightmare.
It really is the core problem. Quantum systems are unbelievably sensitive. They even showed special metal shielding, mu metal, just to block out the Earth's magnetic field.
Wow.
So, yeah, preventing errors or correcting them when they happen is basically the main focus for the whole field right now. Making quantum computers practical hinges on solving this.
How do they even try to fix errors at that level? They mentioned redundant encoding. What does that mean? Is it like making quantum backups?
That's not a bad way to think about it, actually. The core idea is you don't store a piece of quantum information in just one physical qubit.
Okay.
You encode it across many physical qubits in a really clever distributed way.
Spread it out.
Exactly. So if one or even a few of those physical qubits get hit by an error, a flip, a decay, the overall encoded information isn't necessarily destroyed. You can still recover it.
But that sounds like it would need a lot more qubits, right? Many physical ones for just one useful logical one.
That's the trade-off, precisely. Current error correction schemes often require hundreds, thousands, maybe even more physical qubits just to create one reliable logical qubit you can compute with.
Oof, that sounds inefficient.
It is currently. And the physical error rates themselves are still too high for truly large-scale, fault-tolerant computation. Progress is being made, definitely, which is why there's excitement, but we're not there yet for commercial viability across the board.
And then there's just the sheer number of qubits needed, going from, what, tens or maybe 100 now?
Yeah, current systems are in that range, roughly 10 to maybe low 100s of physical qubits.
Needing hundreds of thousands or millions for the really big problems. That scaling seems monumental.
It's a colossal challenge. It's not just about making more qubits. It's about controlling them all, connecting them, keeping them cold, doing the error correction, and doing it all without the cost and size becoming completely astronomical.
Right.
We need breakthroughs in miniaturization, integration, control systems. The whole stack. Building more qubits is one thing, but controlling them coherently as the system grows, that's the really hard part.
Okay, huge challenges. But if they can overcome them, the quantum promise sounds, well, revolutionary.
Hmm.
solving things in seconds that take current supercomputers ages.
Millennia, in some cases, yeah. The potential speed up for certain types of problems is just staggering.
What are the killer apps then? Where could this power really make a difference, maybe even impact us directly someday?
Well, there are several key areas people are excited about. Solving really hard mathematical problems is one, the kind that underpin things like encryption.
Okay.
Designing new materials from the atom up. Imagine discovering novel catalysts, better batteries, superconductors.
That would be huge.
Big time. Then there's chemistry simulating molecules accurately, which could revolutionize drug discovery and development, finding new medicines much faster. Optimization problems. Think logistics, supply chains, which is obviously very relevant to Amazon's core business, finding vastly better ways to route deliveries or manage inventory.
Yeah, you can see the connection there.
And cybersecurity, as mentioned, both potentially breaking current encryption, but also enabling new quantum secure methods.
So, potentially transformative across science, industry, medicine. What about the market size? Is this a niche or are we talking big money?
The projections are definitely pointing towards big money. McKinsey estimated something like a $173 billion market by 2040.
Wow, okay.
And even sooner, the current market, maybe $500 million now, is projected to grow to maybe $2.5 to $5 billion by the end of the decade, though that higher end depends a lot on making progress with error correction.
So significant growth expected soon, massive potential long term. It's clearly not seen as just a niche academic thing anymore.
No, the investment levels and the players involved show it's seen as a major future technology platform.
Okay, bring it back to Amazon. What cards do they hold? What specific advantages might they have given their background compared to, say, Google or Microsoft?
Well, one thing mentioned is our deep experience designing custom silicon, custom chips for their huge AWS data centers.
Right, for cloud infrastructure.
Yeah, building the complex control electronics needed for classical data centers involves skills and techniques that are actually quite relevant for building the sophisticated control systems needed to manage quantum processors. That's potentially a real asset.
So expertise in complex chip design and control systems could translate well.
It could. As for the competition, as we said, Microsoft and Google have been at it longer. Microsoft has a deep history in tackling complex software and hardware integration. Google has very strong fundamental physics research roots. It's a tough field.
And the timelines everyone gives seem all over the place. Why so much disagreement on when this stuff will actually be useful?
Yeah, the estimates vary wildly. NVIDIA CEO talking 15, maybe 30 years.
Okay, long term.
Google sounding more optimistic, maybe 5 years for some commercial uses. IBM targeting around 2033. Some experts think we might see useful demonstrations, say in materials science or chemistry within 5 years, but truly fault-tolerant machines that can tackle anything. Maybe 10 years, maybe more.
So it really depends on breakthroughs, especially in errors and scaling.
Exactly. The uncertainty reflects just how big the remaining scientific and engineering challenges are. It's research, right? You can't perfectly schedule breakthroughs.
It definitely underlines that this is a long-term bet. Very patient capital needed.
Oh, absolutely. This isn't about next quarter's earnings. The massive R&D spending might not show significant returns for investors for, at least 5, more likely 10 years, maybe even longer. High risk, potentially immense reward.
They also mentioned AI briefly, a connection between AI and quantum.
Yeah, there's this interesting potential synergy. Quantum computers might be able to generate unique kinds of data or solve optimization problems that could help train better AI models.
Ah, quantum for AI.
Right. And conversely, AI and machine learning might help us build better quantum computers, maybe designing control pulses, finding better error correction candidates, analyzing experimental data, that kind of thing.
So they could help each other develop.
Yeah.
Interesting. And Amazon's specific path forward. The report hinted their approach is a bit different. Any more clues on what that means?
Not a huge amount of detail, but the implication was their strategy isn't just mimicking others. Their focus on those cat qubits we talked about, trying to build in error resilience at the hardware level, that seems like one key aspect.
Okay.
It suggests maybe a different bet on the best way to get to fault tolerance. It's a valid approach, looks promising on paper, but like all these strategies, the proof will be in the pudding, as they scale it up.
And it sounds like Amazon's leadership gets it.
Yeah.
That this is hard and it will take time.
Yeah. The report stressed that CEO Andy Jassy and others have been clued in from the start. They understand the difficulty and the long horizon, which is important, right? You need that top-level buy-in for such a sustained, expensive effort. The feeling was that even being a later entrant doesn't necessarily put them out of the running, precisely because the field is still so nascent and their commitment seems solid.
Okay, so let's try and wrap this up. Summing up this deep dive, Amazon is seriously in the quantum game now.
Definitely. A major player alongside Google and Microsoft.
They have their own chip, Ocelot, focusing heavily on reducing errors using novel things like cat qubits.
Right. Tackling that core error correction challenge, potentially with a slightly different hardware-first philosophy.
But the whole field faces huge hurdles, error rates, scaling up to millions of qubits. It's a long road.
A very long road, but with immense potential payoffs. Materials, medicine optimization, the list goes on. Market potential in the hundreds of billions down the line.
And Amazon seems committed for the long haul, leveraging their chip expertise and backed by leadership that understands the challenge.
Exactly. So while quantum computing might still feel like science fiction sometimes, it's very much a real focus of intense R&D and investment for these tech giants. And for you, the listener, understanding this shift is pretty key to grasping where technology might be heading next. It's about the future of computation itself.
Right. It's about staying informed on these potentially world-changing shifts. Okay, on that note, maybe a final thought for you to chew on. Think about the really tough problems out there. In science, in industry, maybe even societal challenges. What currently impossible problem do you think quantum computing might, just might, unlock someday? What solution is waiting just beyond the reach of today's computers? Something to mull over.